Okay, hello again, Year 10. This is the video for Year 10 Triple Chemistry for your lesson 1 of week 4, which is the week beginning the 29th of June. Your first chemistry lesson of that week, as I say. So, just before we get on to the subject matter for this specific video, we're going to just quickly have a go at some questions based on what we did in the last video. So if you want to pause this one and have a go at these on my laptop. Let's do this, there we go. So if you want to pause it and have a go at those, then we'll go through it. Okay, so number 1, what needs to happen between the particles of the reactants for a reaction to take place? Well, the answer is we need collisions between the particles of reactants, and we need those collisions to take place with a certain amount of energy. More of that in a moment. Number 2, what are there more of if a substance is more concentrated? Well, if a liquid is more concentrated, there will be more particles of the substance in that liquid. So for example, if you have a more concentrated acid, there will be more acid particles in a certain volume of that acid, if it is more concentrated. Number 3, what do the particles of the substance have if it is at a higher temperature? The answer is they have more energy. Number 4, what do the particles in a substance do more if the substance is at a higher temperature? The answer is they move more. They transfer thermal energy into kinetic energy. So in a hot liquid, for example, the particles will be moving around more quickly than in a cooler liquid. Number 5, what do we call the minimum amount of energy required in a collision between particles for a reaction to take place? We call that the activation energy. Remember from the last video, every reaction has a certain minimum amount of energy that needs to be present, or the particles need to have a certain minimum amount of energy in their collisions for the reaction to take place. That will be different for different reactions, but every reaction has a minimum amount of energy needed for that reaction to take place. Collisions occur all the time between substances, but if there is not enough energy, a reaction won't take place. Paper burning being a good example. When paper burns, it reacts with oxygen. If you hold a sheet of paper in the air, oxygen particles collide with it all the time. Unless there is enough energy, so you heat that up with a flame or something like that, the reaction between the paper and the oxygen will not take place. Once you give it that energy by heating it up, it will start to take place, and that's when the paper catches fire. Okay, moving on then. So, we're going to look at hydrocarbons. So, there's the key facts from the fact book that hopefully you're sitting with in front of you, or certainly you're going to look at before or during watching this video. And those are the things that we're going to go through, just not very quickly, but briefly in this video, and hopefully we can add some understanding to those. So we're looking at hydrocarbons. Now hydrocarbons are compounds that we get from a substance called crude oil. There is more on that in the next video, so don't worry about that process at the moment. We will go through it in detail in the next video. They're called hydrocarbons quite simply because they contain hydrogen and carbon. They are compounds made up of those two elements in varying proportions, and it's as simple as that. Now, why do we group them together, or how do we group them together? We group them together because they are what we call a homologous series. That means they are a group of chemically similar compounds. So they're not all the same, all the different hydrocarbons aren't exactly the same, but they are chemically similar. They can also be represented by a general formula. So with each group of hydrocarbons, there is a general formula you can apply to it that you can use to identify what type of hydrocarbon something is, and also what proportion of carbon and hydrogen it will have. And that is different for each group, but the hydrocarbons within that group can be described with that general formula. They have physical properties that change gradually as you move through the series. As the proportions of carbon and hydrogen change through the series of hydrocarbons, the properties change slightly as well. Okay, so some of the hydrocarbon series that we're aware of are some called the alkanes, the alkenes, and the cycloalkanes. We are going to focus on the alkanes, so don't worry about the other two just now. We are looking at the alkanes. So the general formula for the alkanes, we just mentioned that, is H2N plus 2. What that means is, however many carbon atoms there are in an alkane, there will be twice as many hydrogens plus 2. Okay, so however many carbon atoms you have, it doesn't matter how many there are, if it is an alkane, it will have twice as many hydrogens as carbons plus 2. That's the general formula that you can apply in order to figure that out. Okay, so looking at some examples, you do need to know the names of some. You also need to know the formula used to describe them as well. So, the alkane with 1 carbon and 4 hydrogens, remember we said CnH2n plus 2, so if it has 1 carbon, that means it has twice as many hydrogens, so 2 plus 2, 4. 1 carbon, 4 hydrogens. That alkane is called methane. Okay, it can be represented either diagrammatically like this, or as a formula CH4, which tells you it's got 1 carbon and 4 hydrogens. Okay, if an alkane has 2 carbons, we call it ethane. Okay, again, it has 2 carbons, CnH2n plus 2, so 2 times 2 is 4, so 4 hydrogens plus 2 is 6. Ethane has 2 carbons, 6 hydrogens. Propane is the alkane with 3 carbons. Okay, so 3 carbons, we know that the general formula CnH2n plus 2, so 3 times 2 is 6, plus 2 is 8, so it must have, if it has 3 carbons, it will have 8 hydrogens, using that general formula. Okay, now because, if you look at these molecules, or you look at these diagrams, every single bond is a single bond. There are no double bonds. What that means is, there is no space, there is no way you could have any more hydrogens bonded into these molecules. Each carbon has 4 single bonds, 1 to another carbon, and the others, or in some cases 2 to other carbons, the others to hydrogens. There are no double bonds, there is no space in any of the molecules for more hydrogens. So we say they are saturated. If something is saturated, that means you can't get any more of something into it. And these hydrocarbons are saturated because you cannot get any more hydrogen into the molecules. There are only single bonds, so they are saturated, and that tells you that they are alkanes. You see a hydrocarbon molecule and all the bonds are single bonds, it is saturated, that means it's an alkane. Okay. You need to know the first 4. So you need to know methane is the one with 1 carbon, and you need to know it's CH4. You need to know ethane has 2 carbons and 6 hydrogens, 2 carbons, and it is C2H6. You need to know propane has 3 carbons and it's C3H8, and you need to know butane, which is 4 carbons and is C4H10. You need to know the names, the formula, and you also need to be able to draw them in this way. You wouldn't be expected to draw a diagram like this, but you would be expected to possibly complete or draw the structure of any one of those 4. Okay. So, as we said, you can represent them in various ways. The 3D full structural formula, which you would not be asked to draw, but you may be asked to identify from. The 2D structural formula, which shows you in 2 dimensions, as it says, the layout of the molecules. Each one can be represented in those ways. Okay, full structural formula, shortened structural formula, which literally just tells you how many of each there is, and then what we call the molecular formula, which presents it as you would see it in the molecule. Okay, so we've got methane and propane there. Methane, 1 carbon, 4 hydrogens, CH4, CH4. Propane, 3 carbons, 8 hydrogens. So the shortened structural formula, without drawing it out, would be CH3, which is that part, CH2, which is that part, and CH3, which is that part. And then it can be represented as C3H8 for the molecular formula. Okay. So they share chemical properties. They all have single carbon-to-carbon bonds. They all end in ane, A-N-E. They are all what we call saturated hydrocarbons, and they share the general formula that we spoke about. So, I'm going to pause the video and have a go at filling in the gaps on this table. Okay, so methane we've spoken about, the molecular formula is CH4, shortened structural formula is CH4, there's the full structural formula. We'll talk about the boiling points in a moment. Ethane, C2H6, shortened structural formula then would be CH3CH3. The full structural formula shows you that, CH3CH3. The boiling point, you'll notice, is slightly higher than the boiling point of methane. Okay, propane, C3H8, CH3, CH2, CH3 is the shortened structural formula. You can see that in the full structural formula, CH3, CH2, CH3. Again, boiling point slightly higher than ethane and higher again than methane. Okay, if you want to pause it and have a go at these then. Okay, butane, molecular formula C4H10, shortened structural formula CH3, CH2, CH2, CH3. And you can see that, each of those parts in the full structural formula. Again, boiling point higher than the previous three. Pentane, 5 carbons, C5H12, using the general formula you can figure that out. Shortened structural formula CH3, CH2, CH2, CH3, which you can see as you go along the full structural formula. Again, boiling point higher than the previous. Hexane, C6H14, CH3, CH2, 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 CH3. And again, you see that pattern as you move along the structural formula. And again, the boiling point is higher than the previous. And then the last two that you would encounter are going up to the 7 and 8 carbons. Heptane, if you want to have a go at these two. Okay. Molecular formula, C7H16. And then again, the shortened structural formula shows you how each part of the molecule is laid out. The full structural formula shows you the full picture. Again, the boiling point higher than the previous. And octane, C8H18, same idea. The shortened structural formula shows you how the carbons and hydrogens bond through the molecule, and then you can see that in the full structural formula, and it has the highest boiling point of the ones we've looked at so far. So, the properties of the fractions are, that you need to be aware of, are how flammable they are, which is how easy they are to light or set fire to, and also what we call viscosity, which is how thick they are or how easy they are to pour. And basically the pattern in that is, as the molecules get larger, so as you get more carbons and hydrogens in each molecule, so as you go from methane to ethane to propane to butane and so on, they get harder to light. So the smaller molecules are easy to light, the larger alkane molecules are more difficult to light, and they get thicker. Now that would make sense, because in an alkane with large molecules, it is thick. It's what we call very viscous. It is difficult to pour. So you start with the small molecules that are runny. They're not very viscous. They have a low viscosity. As the molecules get bigger, as the number of carbons and hydrogens in the molecules increase, as you go through them from methane up to octane, being the ones that we just looked at, they become harder to pour. They become more viscous. So that is the trend in the properties. As the molecules get bigger, they become more difficult to light, to catch fire, they become less flammable, and as the molecules get bigger, the alkanes themselves become more viscous, they become more difficult to pour. Okay, now we use alkanes as fuels, predominantly, and when you burn an alkane completely, you get carbon dioxide and water produced, as well as obviously the energy that you want from burning a fuel. So we can prove that with that piece of equipment there. You might want to draw that diagram or take a note of it, but it shows you the energy is released, because obviously you have heat and light here, and then here you would see water condensation in the tube, and the lime water would turn cloudy to show the presence of carbon dioxide. So if you burn hydrocarbons completely, those are the two products, along with the energy that you want to be released. We'll also look at equations for that combustion, and you can take a note of those. So, there are the key facts. Hopefully that's helped. Thank you.